Right now you can see a typical ultrasonic atomization process realized in repowder, ultrasonic atomizer by AMAZEMET. How to transfer the ultrasonic energy to the melt and provide wetting effect and atomization effect. That is really a challenge, and our team got over 16 patents and applications regarding different solutions how to handle this issue. Right now, through this episode, I will explain to you how different types of Sonotrodes are operating and how to take best out of repowder system, showing what are different systems of the Sonotrodes and how they are operating. Right now in the screen you can see our typical movies. A melt pool agitated with ultrasounds, powder being sprayed, but how the elements that are actually transferring the ultrasounds into the melt are composed. What are the nature of those elements, how they operate, what are the different types of the Sonotrodes. Here we have several different types of Sonotrodes. I would like today to explain how they are used, how they are composed, and what are their pros and cons. First, we'll start with definitions. We call them Sonotrodes as an analog to electrode, but instead of passing electric current, we are transferring mechanical vibration to the element that we are actually processing. People are using different names. You can know those by, for example, ultrasonic horns, ultrasonic probes, and many other different names, but usually they are the very same elements. They are mechanical elements vibrating within a resonant frequency, capable of transferring mechanical vibration into the piece that we are actually processing. Mostly people are using those for welding or cutting with ultrasounds. In our case, we are exposing those to elevated temperature, to molten metals to provide spraying effect and ultrasonic atomization. Here we can see several different Sonotrodes. I will explain later what are the different types of Sonotrodes, including plate Sonotrodes, rod Sonotrodes. There are multiple challenges associated with Sonotrodes. If you imagine that within a single minute of operation, they have at least 1 million cycles of fatigue at elevated temperature, that is really challenging condition for any mechanical element, for any material to sustain during material processing. Today, I will explain how they are operating and how we can keep them within the resonant frequency and without cracking. First, we'll discuss how the Sonotrode is actually operating. In this slide you can see a simulation of a typical rod Sonotrode. You can imagine it's kind of a barrel. We compress it, it bulks, and then we have a tensile part and it shrinks. So basically the rod Sonotrode is constantly being deformed into this barrel-like shape. In the middle of the Sonotrode we have a part we call node. The node is the part of the Sonotrode that is most stressed. There is zero amplitude, zero deformation within the axial direction, but there is maximum stress. On the other hand, on the top and the bottom of the Sonotrode, we have so-called antinodes. There, amplitude is maximum, but stress is zero. To enable proper operation of the Sonotrode, we have to keep the node, the middle part of the Sonotrode, cool. Otherwise, the fatigued material is both exposed to mechanical vibration and enormous heat. Basically, any material can vibrate well when it's cooled down or at low amplitude. But if we expose it to elevated temperature, it cracks almost immediately. Our patents, our know-how, and our IP is related mostly to keeping the Sonotrode cool within the parts that are really stressed. The most important point we have to bear in mind that keeping a Sonotrode cool in the node enables its proper operation during ultrasonic atomization. We could have molten metal on the top. At the antinode part, it could be exposed to enormous temperatures, plasma, induction. It can be completely molten, but If we keep the node cool, the Sonotrode can still operate well and can still transfer ultrasonic vibration. Right now in the slide you can see one of our patents. It is related to cooling system and sealing system of the Sonotrode cooling part. Basically, we're trying to keep sealings as close to the antinode, as close to the heat exposed part as possible, to keep the middle part as cool as possible. Then it is possible to keep ultrasonic frequency within the limits of the transducer and avoid too much heat exposure, cracking and damping. Sealing of the Sonotrode itself is kind of a tricky task. If you imagine that this part is vibrating 60,000 times a second, it is really hard to get it sealed the way that the cooling liquid is not leaking through the sealing devices. In our case, we use several different types of sealings, different types of cooling systems, but the most important are those composed of ceramic materials. Having ceramic seals, we are enabling to keep it as close as possible to the heat zone and keep the middle part of the Sonotrode cool. Getting sealing and cooling system as high as possible, as high to the antinode, enables proper operation of the Sonotrode. In here you can see several different types and sizes of the Sonotrode. You have to bear in mind that the Sonotrode itself is vibrating within the resonant frequency of the transducer that we are using. Higher the frequency, shorter the length of the Sonotrode. For example, in here you can see three different Sonotrodes: 20, 40 and 60 kHz. Low frequencies are much easier to cope with heat. There is a lot of space to have our sealings, cooling system. The Sonotrode itself is bulky, but higher we progress with ultrasonic frequency to reduce particle size distribution, those Sonotrodes are getting finer and finer. So for example, 60 kHz Sonotrode is as little as 1/3 of the 20 kHz Sonotrode. And keeping it cool and keeping it cool at the node is much harder task than in case of 20 kHz. The other thing that we have to understand about the Sonotrodes are materials they are composed of. You can imagine a Sonotrode as a spring with certain key factor. Higher the key factor, higher the stiffness, larger the stress within the Sonotrode. Also, higher the displacement of the spring, higher the stress within the Sonotrode, our spring itself. So, there are several elements that affect the stress within the Sonotrode. First, just as a reminder, the most stressed part, node, the middle part of the Sonotrode. If we want to calculate what is the stress there are three most important factors. First, the amplitude. It is basically linear with the amplitude. Higher the amplitude, higher the stress. But there we have to bear in mind material. If we think about the spring, the Sonotrode, as our model, there are two main material properties that determine what is the stress inside. Stiffness, our Young modulus, and density. Basically, higher the density and higher the Young modulus, larger the stress within the Sonotrode is. So for example, within tungsten or tantalum Sonotrodes, stress is enormous. Although they are refractory materials, they are very hard to vibrate due to large stiffness and large density. On the other hand, titanium, especially beta titanium alloy, are low in density and low in modulus, so they are much easier to vibrate. The maximum stress could be order of magnitude lower than in case of heavy refractory metals. In the slide you can see a table of several different base materials that we use for Sonotrodes and what is the maximum stress in the node. For example, aluminum, very light, very low Young modulus. maximum stress at certain amplitude, only 48 megapascal. While the same conditions, tungsten heavy alloy, over 340 megapascal there. So, considering design of the Sonotrode, we have to bear in mind that not only the material resistance, thermal resistance, but also dynamic properties, stiffness and density are important to keep it vibrating well. Otherwise, we could have material which is, in theory, much more resistant to elevated temperature, but due to density and stiffness, the maximum stress will be higher, so the ultimate performance of the Sonotrode will be lower. Designing Sonotrode, cooling it down, is pretty a challenging task. In this slide you can see two thermal simulations of very same Sonotrodes, the left one composed of copper-based alloy and the right one composed of titanium-based alloy. Both the very same dimensions, the very same heat flux of the plasma, but due to thermal properties, heat conductivity, there are completely different thermal profiles in the Sonotrode. Copper, due to high thermal conductivity, is kept almost completely cool. It is much easier to keep node at lower temperature, while titanium, on the other hand, as thermal isolator, it is aggregating, it is accumulating heat, and it's very fast getting out of frequency, and it's getting to temperatures where damping becomes an issue. That's why creating composite Sonotrodes and choosing right Sonotrode for proper application is essential to keep ultrasonic atomizer working. To wrap it up, what is the best type of Sonotrode? There is not such thing. Each and every material, each and every ultrasonic atomization process requires certain type of Sonotrode that have to be carefully and thoughtfully designed for such experiment. Thank you so very much and see you in the next episode.